Okay, good afternoon, everyone. May not be afternoon from where you are joining us from, but thanks for joining us today for this proposal planning workshop. I've launched a poll to hear about you and where you're from and what you're up to these days, just for us to know a bit who attends these. So please do fill that out. Other than that, let's go ahead and get started. So I'm going to give an overview of the GBT capabilities, how you observe with the GBT, and a little bit about the current proposal call. So the goals of this workshop were as advertised. We'd like to train new GBT users and teach you how to propose for time on this fantastic telescope. And then we also want to provide an update on some of the most recent GBT upgrades and capabilities. So today, as I said, first, I'll provide an overview of the GBT, and then Ryan will be providing an update about the ultra wideband receiver. And then we'll hear about the sensitivity and mapping calculators, how you use those. And then lastly, Jesse will be providing an overview on how you use the proposal submission tool and giving some submission tool results. And we do have an office hour coming up on Friday that if you have more questions, you can join us during that time to ask some more detailed questions. And also those that may be watching this recording, please do join us for that office hour. And the recordings of all of the talks today will be made available on our workshop webpage and on the GBO YouTube channel for you to peruse later. So let's get started on the overview of GBT. So I'll give an overview of what it is and just general specs of it, what the science areas are that are mainly used, that use the GBT, and then some of the capability and performances of the GBT. And I'll go over the observing strategies that you want to consider when you're proposing for time, and then I'll go over the current proposal call. So Green Bank was the original National Radio Astronomy Observatory site and has been operating for many, many years, 70 years now, actually. And there are all of these different types of telescopes, radio telescopes that were here. It's a very historic site, but the main one that most people know about and use is the main Green Bank telescope that was completed in 2000. And then in 2009, we had a surface improvement for the high frequency specifically. One thing that is particularly interesting and unique to the GBT is the radio quiet zone. And this was established by the Federal Communications Commission, the FCC, and also IRAC in the 1950s to minimize harmful transmissions from various things and devices of modern life that transmit. So that's things such as cell phone towers, cell phones themselves, radios, the radios on planes and transmitters between planes. So there is this 1,300 square mile protected area around GBO and also Sugar Grove to protect our receivers from a lot of radio frequency interference. That's what we call it, RFI, that interferes with scientific observations. So yeah, we really try to mitigate the RFI that is in the GBT data. So this is a quick overview of the capabilities of the GBT. So one of the main things, it's a 100-meter diameter unblocked dish. So it is currently the world's largest steerable radio telescope. And the feed arm is off axis. So this means that the feed arm does not actually block any light that is coming in. Typically, you'll see a design here that I show on the right, where you have the receiver and subreflectors and things in the center of the dish with arms supporting it. With the GBT, we have this off-axis arm so that you can get full effect and of the dish. The receivers cover a large frequency range. We have many different receivers, and covers from 0.1 to 116 gigahertz. And this is over 2 orders of magnitude, and it crosses over with the VLA and ALMA as well. It is particularly excellent sensitivity for point source and extended objects because of the large collecting area of the dish. So this is a great thing to use for science, for sensitivity for point sources and extended objects. It covers about 85% of the total sky, and so you can observe most of the total sky. And that's useful because, or that's created because it's a movable structure. And as I mentioned before, another great thing about the GBT is it's located in the National Radio Quiet Zone. So there is less RFI than you might find in VLA or ALMA data. And as I mentioned, in 2009, we had an upgrade for the GBT where the active surface was upgraded and installed. And so what this is that we have 2,000 and about 210 actuators that are located on the corner of all the panels. And there are 2,000 panels, so you can see an image of this here. And this allows us to manipulate the structure of the surface of the dish to apply corrections to allow high frequency observing. So you can imagine that at high frequency, you have very short wavelengths, and the perturbations in the disk can really affect your observing. So we can correct for this with these actuators, and we can then achieve a surface RMS about 230 microns at night due to this active surface that was installed. So it is fully steerable in both. We have 2 degrees of movement. You have azimuth and elevation, and you can observe up to about 5 degrees above the horizon, though this is different for different instruments. Typically, maybe more about 15 degrees of elevation, but these, we have pretty good slew rates. So the azimuth goes about an average of 35.2 degrees per minute, but though that gets cut in half when the temperature goes really low because it actually affects the movement of the oil, as it's difficult to actually move the telescope. And then the elevation limits are about an average about 17.6 degrees per minute. And I will also point out that you may actually now see in the bottom left-hand corner of the slide that there's an answer to one of the questions in the poll that I previously put up. Okay, so this is the fantastic large range of scientific areas that use the GBT to study various science objects. So we have a lot of pulsar science going on, particularly by nanograv. There's a lot of science being done with neutral hydrogen. You can get the masses and kinetics of local galaxies. Some cosmology and high redshift work, galaxies, galaxy clusters, carbon in the early universe. We do a lot with astrochemistry. A lot of molecules have been observed for the first time with the GBT. A lot of people use the GBT for studying quasars. And star formation is very popular too, ammonia mapping, and just observing cold and dense gas tracers. Some people use it to study basic physics and also the solar system. We may have more radar soon as well. So planetary radar is a big area of science here. And then of course, SETI. There's a project called Breakthrough Listen that they get some guaranteed time on the telescope. And then also people use the GBT to study fast radio bursts, though we are currently in the process of building an annex of CHIME, in fact, and so the site will be used for that as well. And we were mentioned in the 2020 decadal survey. So the decadal report endorsed GBO as an essential facility and recommended sufficient funding to maintain and improve its capabilities. So we were named in the decadal survey, which is a survey that is done every 10 years by the National Academies of Sciences, Engineering, and Medicine, and they advise the United States Congress on what to fund, what large projects to fund in science, and what specifically astronomy, and what astronomical instruments and areas of interest are should we focus on in the next 10 years. So it was mentioned pulsars, gravitational waves, time domain, and multi-messenger astronomy, biochemical signatures for life, and then origins and evolutions of stars and galaxies. So that covers a lot of our main science areas that are used for use the GBT. Here's a quick breakdown of GBT science in the ASTRO 2020 decadal survey. So this was the number of white papers that either explicitly mentioned the GBT, mentioned GBT science, or just implicit and explicit mentions. So the GBT is a very capable and relevant instrument for the next decade. So here is a quick summary of the GBT specs, the coordinates, the optics, and you'll want to check out the proposer's guide, which is easy to find on the website. And this gives a lot of these main specs and all the information that you might need to know about it, the elevation limits, the declination range, et cetera, and some of the things I already said. So we have two different types of receivers on the GBT. We have the prime focus receivers, which there is this boom, which is shown in this picture, and it actually rotates out and goes into the prime focus of the telescope. And there are several different prime focus receivers, which I'll go through later, but only one of those can be on that boom at a time, and they get switched out on maintenance days. And then there are the Gregorian receivers, which are held in the Gregorian receiver cabin, which is pointed to here in this image. And the light from the main dish bounces off the subreflector and down into the Gregorian receivers, and the turret, it rotates to put different receivers in focus. And these are typically higher frequency instruments, and you can have 8 receivers in a turret, on the telescope at any time. So how we do this is we have maintenance days during the fall, winter, and spring. We have 1 day a week where we shut down the telescope and do maintenance and switch out receivers. And in the summer, we have quite a few more maintenance days. So here are the prime focus receivers. There are quite a few of them. The main ones that get used are the 300 megahertz and the 800 megahertz. The 450 and 600 overlap with a lot of digital TV signals. So there's a lot of strong RFI. If you want to use this, you should contact a support scientist before submitting a proposal. We also have another prime focus receiver that has various bandwidth options, but yeah, and also for these prime focus receivers and for the Gregorian receivers, the receivers that are on the telescope are determined by the demand of the accepted proposals. So we have a scheduling system that schedules observations, and also we switch out the receivers if there's a lot of proposals that requested 800, that one will be on the telescope more often than 342. And the same with the Gregorian receivers. So we have another prime focus receiver that is coming into play soon. And Ryan is going to talk to us about that a little bit later, but it's the ultra wideband receiver. It has a very large bandwidth. It's optimized for high precision pulsar timing and wideband observations of fast transients. And it's being commissioned now and in the fall, so it affects the availability of the prime focus receivers. And as I said, Ryan will be telling us more about that later. So here are the 11 Gregorian receivers that we have, and a lot of different science that can be done, a lot of frequencies. So I'll just quickly go through these. So the L band receiver has that frequency range. It has a notch filter in that specific range there to suppress the really high RFI. And then we have S band and then also C band. And we recommend to do linear polarization, and the circular polarization is not recommended currently to use for C band. X band, the polarization purity degrades above 10 gigahertz, but in fall of 2020 of this year, 2022, there'll be a new X band receiver going up. Not much will be different, except that there'll be improved gain at higher frequency and a little bit larger bandwidth. Our KU receiver has 2 beams, and then the KFPA, which stands for the K-band focal plane array. It has 7 pixels associated with the camera. It's really good for mapping, so it's a multi-pixel receiver. And yeah, so you have multiple pixels on the sky at once. And in the narrowband, you can have narrowband mode or broadband mode, but with the broadband mode, you can only have the 1 pixel. It might be possible to use both beams at the same time, but we're still working on that. But anyway, you have the narrowband mode and the broadband mode for KFPA. And then KA band, again, we have 2 beams, each with a single polarization, and they're each broken up into 3 subbands. And then we have Q band, which also has 2 beams. W band has 2 beams, each with 4 different subbeams. And then Mustang 2 is a bit of a special instrument. It was commissioned by the University of Pennsylvania, and it's essentially a continuum observational instrument. It's a bolometer camera, and it is a shared risk instrument. So you must have permission from the Mustang team to propose for it and use it. If you have any questions about that, let me know. I'm on the instrument team for that. But it is not officially supported by GBO, but can be on the telescopes. That's why you have to have the permission of the team to use it. And then lastly, we have Argus, which is a multi-pixel receiver, 16 pixels, really good for mapping. And it has 1 polarization. So that's an overview of the different receivers that we have that are higher frequency than the prime focus receivers. And 8 of these can be on the telescope at a time. And this is dictated by the proposal pressure for different receivers. So again, in the proposer's guide, there is a table that has a summary of all of the available receivers, the band, the frequency range, the polarization you can use, the number of beams and polarizations per beam. So check that out for your desired science. And it has also information about the beam separation, the full width, the half max, and instantaneous bandwidth that you can use then for calculating how much exposure time you need. So as I was mentioning, there is only a certain number of receivers on the telescope at a time. So most of the most popular receivers are available most of the time. So that's L band, X band, Mustang 2, Argus, and KFPA. And the ultra wideband instrument is still being tested, and the X band receiver is also being currently commissioned, etc. The less popular receivers will be made available, but for usually high-ranking proposals that come through. So those will be made available on a less frequent basis. And here's an image of what it looks like underneath the Gregorian receiver turret. So we have a couple different backends that you can use. Vegas is the most used. This is what you usually use for observing spectral lines and also pulsars. And then there is the digital continuum receiver, or the DCR, used for continuum. We have the CCB and a backend used for VLBI, and then a radar backend and the breakthrough listen background. you will probably most likely be using Vegas or the DCR, maybe the VLBI. So for Vegas, there are different spectral line modes. Again, you can see this table in the proposer's guide. And the Vegas mode determines your bandwidth and your resolution. So yeah, there are 29 modes. Each mode corresponds to a different bandwidth and resolution. And your science will dictate what you need and which mode you need to use to make sure that the spectral resolution that you get gives you the velocity resolution that you want. And some modes use subbanding, and these modes will be used in the sensitivity mapping calculations that we will go over later. So think about your science, what spectral resolution you need, velocity resolution you need, and that will determine the mode that you need to use. There's also a pulsar mode that Vegas uses, and there are coherent and incoherent dedispersion modes. So the incoherent are the spectra are written without any removal of intrachannel dispersive smearing, and the dedispersion must be conducted offline in the data reduction, whereas the coherent, the dispersive delay is removed prior to detection, providing a higher effective time resolution. So this requires prior knowledge of the source. So there's a lot of different modes. I would recommend reaching out to a support scientist for help with this, with the various modes and things for observing pulsars. So now I'd like to go over a few observing strategies that you should consider when you're writing your GBT proposal. It provides a lot of observing options, multiple instruments, and different modes according to this. So first, you'll pick a receiver based on the frequency that you want to observe. And then you'll pick your back end based on the observing type, whether you want spectral line, continuum, pulsar, etc. And then you'll pick your observing techniques based on your science goals. So if you are observing a point source, a large field, narrow or broad lines, I'll go over that a bit later. And then your calibration strategies will also depend on receiver and science needs. So high frequencies, we have to do something called auto-OOF, where you actually correct for the structure of the dish. Gregorian, you have to make focus corrections because you're using this subreflector, but prime focus, you don't have to make those corrections because it's at the prime focus. So let's go through a few of the main observing modes and strategies that you use to derive your reference data. So first you have frequency switch observations. So this is when you obtain blank sky by keeping the telescope pointed at the same object, but simply switching the center frequency of the measurement. So you're switching the local oscillator. So you can see that here in the left image where you have the line that's shifted by a certain amount. And then later in data reductions, you do a rather sophisticated, effectively a subtract and divide to combine this information to produce your spectral line. You can do in-band or out-of-band frequency switching. It's based on your science. But yeah, in post-processing, you correct for this and obtain your spectral line. For this, you do need a priori knowledge, like the redshift, so that you know how much to switch by and that it won't interfere with your observations. So when should you use this? The two main uses are to increase the on-source integration time by performing in-band switching. This reduces the amount of time spent slewing to an off point, so to a different point in the sky. You could just switch in band. And it also allows the observer to avoid having to find an emission-free reference position when observing in an area that could be riddled with it. So that helps. So if you have a narrow line observations in a clean, non-crowded area, this is a good time to use that. A good time to use this is these galactic H1 observations where there's a lot of galactic H1 everywhere. So there, it's hard to find a place to actually move the telescope to derive reference data. There are advantages and disadvantages. Your advantages, as I said, you don't have to spend time slewing the telescope and you don't have to find an area free of emission. The disadvantage is you have to have a good constraint on the redshift, and the system must be stable, and it can produce significant standing waves in your data. So this is frequency switching. And then we have the more intuitive, I think, position switched observations. And this is, as I've made this schematic here, you point at your source, and then you slew the telescope to a different place that is free of emission and use that as your background. And that's what this looks like. And you effectively then can just subtract out the off source and derive your reference data. And you can kind of see actually about 4,500 kilometers per second. You can see there's a little blip there in the T source plus everything else, so the on versus the off, and then basically subtract it out and you get your line that you are interested in. So when would you want to use position switching? Well, this is a time when you might want to use this, that you have a crowded spectral region or significant RFI. So you would want to be able to really make a good off source and reference data. And you can also use it for broadline observing, because if you were to frequency switch a broadline, it could shift it out of the bandwidth. And this is a good way to get the best baseline measurements possible. It's good for observing compact sources as well. What's great about this is you don't have to know the redshift of your object. It typically gives really good results. But the disadvantages are that it requires repointing of the telescope, and you have to carefully choose your reference area, and your source can't be too large or extended that your reference data would have your source in it. So then the last one is this dual beam position switching. So this is called nodding or sub-beam nodding. But effectively, you are switching which beam. So it's dual beam, so it's the receivers that have two beams, and you can have one beam be your reference and one beam be your on source, and you can effectively switch between those to derive your reference data. And you can only use this with multi-beam receivers. It's useful when you're observing something that's angularly small and your source can't be beyond the beam size. So again, here are the three different types of observing strategies. So again, based on your science, you'll choose a different observing mode to use. And here's a quick summary that you can use to decide what you'd like to use. So if you have a source size that's smaller than the beam, it's a line observation, and you're using position switching, here are the various things that you can use for different receivers. This is what you'll see actually in the Astrid scripts. You have the nodding, which is you're moving the telescope, sub-beam on using this sub-reflector. On and off, you're actually moving the telescope. And then tracking is you're just actually tracking the source. So if you have a source size that's less than the size of the beam and you're frequency switching, then you'll get a track scan. And then if you're doing continuum observation, you'll have something called a daisy map. And you'd think with a compact source, you wouldn't have to map, but daisy mapping is an effective way to deal with the 1/S noise you get with long integrations or large bandwidth with the continuum observing. And if you have a really large source, if your map is larger than the field of view of the instrument, you'll have to use, you'll make a deck or RA map, and we'll talk about that later. But if the map is, or the area that you want to map is larger, is less than the field of view of the instrument, you can use these various strategies as well, a daisy, a point map, which is where, well, the RA and deck maps are on the fly, where you're constantly taking data, whereas point maps is where you sit on one point of the sky and take data. So another really important thing of observing and proposing is you have to estimate your overhead time. So here are a quick few things to consider and you could use for your proposal. You should point and focus every 30 minutes to an hour, depending on your frequency, and point and focus takes about 5 minutes. So I've listed here which bands, how often you should point, and during the day versus during the night. And hopefully that will be useful to you in your proposal writing process. Auto oofing. So this is for the high frequencies. This is where we basically look at the errors on the dish and then apply a correction. And this is done through auto oofing, but this takes about 30 minutes. It's used to correct the surface for thermal effects in these different bands. So when you move a telescope around, gravity will affect it differently. So we count for that, but then also you have thermal effects, heating and cooling of the earth and of the air will change the shape of the dish as well. So this auto oof accounts for that, and it does take about 30 minutes. We're working on some strategies to decrease that time, but for now you'll have to consider that takes about 30 minutes. And for Mustang, I know we usually have to do it. It's a good night, every 4 hours or so, depending on, you have to monitor how the beam looks, etc. And then you have to oof. So I will say, please do state your logic of your overhead estimate explicitly in your proposal. There's a technical justification section. Please write out just explicitly, we're observing this many targets, and so we need to point and focus this many times, which will take this long. And so we do a total estimate of this for overheads, because as staff, we go through and check that and make sure you have enough overhead time. So it really helps to explicitly see your logic of why you're requesting a certain amount of time and a certain amount of overhead time. So here are some different just pieces of advice on your sources and your sessions. So Jesse will go over this later about how to create a proposal in the PST. But you have to create sessions and you have to put in your sources. So here are some pieces of advice. You should group your sources into sessions. So put several sources into one session, so it's easier, more efficient to schedule you. And then make sure that your sessions are rounded up to every 15 minutes or 0.25 hour. We don't granulate any smaller than that. And you want your sessions to be less than 6 hours. Just for schedulability, it's easier to schedule if it's less than 6 hours. Only include receivers and backends that must be used together in a single observation. So yeah, when you have a session, just use the receivers and backends that go together. Don't try to combine different backends and receivers in one session. And sources should be within about 2 to 3 hours of one another in RA. And yeah, that just helps schedulability. And sources should be visible at the same time for at least 1 to 2 hours. That also helps schedulability. And you want the declinations to be within a few tens of degrees of one another. So what I personally do is I usually just group my sources by RA and due, within 2 hours of each other, et cetera. And then sources with declinations less than the latitude of the GBT should not be in the same session as sources with declinations greater than the latitude of the GBT. This is because of just, how our instrument is set up. Because if you have a source that has a deck above our limit here, and then you go below the limit, there's a lengthy slew times that occur if you have something below the latitude of the GBT and above. So just generally just group those into different sessions. And this is advice, general advice, just based on some things that we've seen. We've seen some people put all their sources into one session. That's pretty hard to schedule usually, depending on how many, or they make each source one session. And so it's really good to try to group your sources together to get them to be easily schedulable. And it may make sense for your science to put each object in a session, but often you do want to combine things together. So our current proposal call is we have a deadline of Monday, August 1st at 5 o'clock Eastern Standard Time. And there is this proposal call link. And we expect that the disposition letters will be sent out in early November. So once you submit a proposal, you'll hear in early November about that. Keep in mind that 2023A observations will begin February 1st, 2023 and go through July 31st, 2023. So make sure your object is observable during that time. We do have an observer training workshop that's going to be held the 3rd through the 5th. And we typically encourage people that are on a successful proposal to sign up for this workshop so that you can train remotely. Currently, the registration is closed for this workshop, but we wanted you to know about that these workshops exist so that when you submit a proposal and get accepted, you know that there is this resource, and we usually hold those in February and in August to help train you how to use this GBT before your observations start. So this year, this school is being held virtually. So we also have the opportunity to do joint proposals with various sets of instruments. So it's possible to submit to another telescope as the primary telescope you're asking for time, and then ask for supporting GBT time. That's what's on the left-hand column. So you're submitting a proposal to that other telescope, and then you can ask for GBT time as a complimentary request. But then you can also submit to the GBT, which is the primary, and the supporting is not the GBT, and it's a different one. And so there are different allocations of these telescopes, other telescopes that you can ask for supporting data from. And so what you get is the primary, and then you can also request the supporting type. In all cases, there's eligible funding for joint proposals, and there are other limits for other telescopes. So consider also asking for some complementary time or supporting time with another telescope. So we have different proposal categories. There are the regular and the large. So the basic difference is either the number of hours and the cadence that you need to observe. So this cycle, we will not be accepting the large GBT proposals. We only accept those in February. So you'd have to wait for the next proposal call for that. But It's typically, for lower frequencies, it's a large proposal is more than 400 hours, and you need to observe at a cadence over a year. And then at higher frequencies, it's if you need more like 100 hours or more, and again, or you need to observe over a year's worth of time. So we have these different regular and large proposal, different classifications. We also have something called triggered and DDT proposals. So triggered are those whose times are unknown. So you submit a proposal, but you don't know when exactly you need to observe because you don't know if your object will be observable. So something like a fast radio burst or some such thing, or something has to happen in order to trigger the observation. So you submit these at the normal proposal call deadline, and they're intended for pre-planned observations of transients whose times are unknown. So you need to include a clear, well-justified trigger criteria. What exactly needs to happen in order to trigger your proposal? And then there's a small amount of time called the director's discretionary time. So these are proposals that, a target of opportunity comes up, something happens in the universe that was unexpected, and you weren't able to submit a proposal at the previous proposal call because you didn't know it existed. So you can submit a target of opportunity, DDT, and you need to observe it right now, sort of thing. And you have to lay out why, what is the unexpected phenomena, and why do you need data now for that. You can also use it as an exploratory time. So it's something that you don't feel that you need to submit a full proposal for. It's more of an exploratory idea that you have, and you just want a few hours just to see if your idea works. So it's intended for pilot projects, taking advantage of a new idea or capability. So it's something that you don't think needs to be a full-blown proposal, but you need to have something to show in the future, in future proposals, that something actually works. We can also do VLBA and GBT proposals. So this is a very long baseline array. So this is where you use multiple telescopes across the world in the US to get really high resolution images. And if you include the GBT with this, with that high resolution image, you won't see the large scale structure. But if you include the GBT, you'll actually be able to see the large scale structure of your instrument, and it will improve the sensitivity overall. There's a specific backend for this, and all proposals need to include overhead estimates in the time estimates. I mentioned that before, but for VLBA with the GBT, you need to include 30 minutes at the start of your observation for setup and pointing. So please do remember that if you submit a VLBA, the GBT proposal. And you can find more information at the links listed below. And okay, let's say you get time on the GBT. Yay, exciting. So your successful proposals will be observed by either the PI or another member on the proposal team. So there are a couple different options. So first of all, you'll need to send someone to the observer training workshop to observe, be able to observe remotely. It would be great if you could send several, so there isn't always one observing. There is also an option if you're an experienced observer and you know how to do things, you can actually create operator run projects. So anything that doesn't require auto OOF can be operator run. So this is starting to be more and more common now. So as I said, the training schools are often offered either January, February, May, and September. This year we had February and August, so around there. So it's around the start of the semester. And we have the one I told you about. And then there is GBT IDL for that you can use for spectral line data reduction. And there are detailed instructions on how to use that. And there is a data reduction pipeline actually as well that you can use. So I created a checklist for you of what do you need to submit a proposal. So you need your scientific justification, which for regular, it's 4 pages, no less than 11-point font, on what you want to observe and why you want to observe it. You have 4 pages. And then you have your technical justification, which is separate from the scientific justification. You need to justify to us your total time request. So why did you request the on-source time that you need? And we request that you include the output of the sensitivity calculator in your technical justification. That helps us reproduce your results and say, yes, this person requested the right amount of time. Or if it's not right, that's okay. We can help change that and help and work with you to get the right amount of time that you need. And then how much time you need to make a map. Again, please put the output of the mapping calculator directly into technical justification, and then include explicit calculations of your overheads, how much overhead time you need and how you got there. And also in the technical justification, you have to talk about the impact of RFI on your data. So you have to acknowledge that RFI will affect you somehow and how you're going to deal with that. You also need to know the RA and DEC and redshift of most of your sources. For the resources section, you'll have to know what receivers and backends you're going to be using. And then for sessions, you'll need to group your sources into sessions with receiver and backend information. So you just need to group everything together, and then that's what gets translated into what goes into scheduling on the GBT. So with the GBT, we use something called the dynamic scheduling system, or the DSS, and it in real time schedules over the next few days based on a lot of different things, but how highest priority proposals, what the weather looks like, and such things. And so it will look at your sessions and then prioritize, and then you will get scheduled. So that is a quick overview of the GBT, how to observe with it, what to consider for your proposals, etc. And I'd be happy to take any questions. Tony Minter is also here to take any questions as well that you all might have. I will also share the results here of the poll. But yeah, does anyone have any questions? Please either ask in the Q&A or raise your hand, and feel free to unmute. No questions? Well, if there are no questions, not at all, not even. Okay, great. Question. Yes. Okay. Let me see here. Okay, I have to move the poll over. Okay, can we be from any part of the world to make a proposal? That's a great question. Yes, you can. We are an Open Skies institution, so anybody can make a proposal, submit a proposal. So yeah, there are no restrictions that way. Well, okay, it seems we have no other questions. So let's take a few-minute break here, and then we'll have Ryan share with us about the ultra wideband receiver. So I'm going to record here the results of the poll and then share them with you. So let's come back in about 5 minutes or so. So if anyone was wondering about the answers to the question, the GBT weighs the equivalent of about 52 blue whales and is the equivalent height of about 27 giraffes if they're standing on each other's head.
Can everyone see the slides?
Yes.
Great. Yeah, so as some of you may have seen in the most recent proposal call, we are planning on having our new ultra-wideband receiver available for use in the 23A semester. I just put some specs here for anyone who hasn't already heard about this. So it's going to cover the frequency range of 0.7 to 4 gigahertz, and we'll be able to do that full 3.3 gigahertz of instantaneous bandwidth with our Vegas backend, and with our DCR continuum backend, but I would not recommend using the full bandwidth to do the 1/s noise with a bandwidth that wide. It'll provide dual linear polarizations, and you'll have the option in the backend processing to form self and cross polarization products so that you can form full Stokes parameters. Our target system temperature is 30 Kelvin. The very broadband nature of the optics of the GBT mean that the system temperature is not going to be as low as our narrower band receivers that cover the same frequency range. So it's not going to have the same kind of RMS at any given frequency, but the very broad bandwidth has benefits for pulsars, for fast radio bursts follow-up, and other types of wideband transients. And potentially, if you have enough spectral lines that you want to observe in this frequency range, you might get a win by being able to observe the full range instantaneously with a single receiver, even though the sensitivity won't be quite as good as, say, just using L-band or just using S-band. I will note that it covers the 3 to 4 gigahertz range where we currently don't have a receiver that actually operates over those ranges because our S-band receiver cuts off at 3 gigahertz. The target gain is going to be between 1.5 and 2 kelvins per Jansky. A little bit more gain at the lower end of the band, and then a little bit less gain at the higher end of the band. And as I already mentioned, it'll be supported with Vegas, both in pulsar and spectral line mode, and DCR. And primarily, I think we'll use DCR for things like pointing and focusing scans, but it will be available for continuum observations in different modes if with different bandwidths if people are interested for that. All existing Vegas modes are supported. That includes pulsar and spectral line modes with the ability to process the full 3.3 gigahertz bandwidth. So right now, we are limited in our ability to do coherent D-dispersion pulsar observations to about 1.25 gigahertz of usable bandwidth, but upgrades to the Vegas backend will allow us to do coherent D-dispersion over the full band along with incoherent D-dispersion pulsar observations in all spectral line modes. And as already mentioned, we plan on it being available in the 23A semester. So those are the specs. I just wanted to go through a few things that people should be aware of if they are going to propose for this instrument. So the current status is that we've achieved first light, but we are still undergoing commissioning. We're actually reinstalling it on the telescope this weekend. And the final performance metrics, the actual final TSIS and sensitivity and gain have not yet been fully measured. So we're still iterating on some of the engineering aspects to try and bring the TSIS down as low as possible. So with that in mind, the receiver is available as an option in the GBT sensitivity calculator. So if you plan on using or proposing for this receiver, you should use the sensitivity calculator to estimate your required observing time. Right now, the sensitivity calculator is using a system temperature which is higher than the target value, just to provide some buffer for time requests in case we continue to have to do a little bit of iteration to get things down to our target level. The good news is that that is a bit of a conservative estimate, and so Hopefully, you'll get even better data than you might expect using the sensitivity calculator when everything is said and done. But please do use the sensitivity calculator rather than trying to use any quoted metrics that you might have found online or in previous talks to estimate your time requirements by hand. RFI, so with a receiver this broadband, especially these frequencies, RFI is a concern. The preliminary data that we have so far seems to indicate that RFI is not going to be any worse than when using other receivers that cover this range. So we're going to see the same types of sources that we normally do, but we're not seeing evidence yet with the data that we have in hand that we're getting any kind of compression or nonlinearities over this broader bandwidth. And I will say that we haven't previously had a lot of data on the RFI in the 3 to 4 gigahertz range. There is some, but it doesn't look terrible. And so standard RFI excision tools should be sufficient. And I've got to put a number in there, but you can expect the effective bandwidth after eliminating some channels that are contaminated with RFI to probably be about 80% of the quoted bandwidth. One more thing I'll note is that there is a permanently installed notch filter from about 2300 to 2360 megahertz. Our S-band receiver has this as well. This is to take out Sirius XM satellite radio, which is extremely strong. Finally, for overhead, the kind of primary science use case for this receiver is pulsar observations, and particularly high precision pulsar timing. And it is being installed at prime focus. In the past, we did not recommend that people do focusing observations when using the prime focus receiver. And the nature of the optics of the GBT meant that you lost very little sensitivity, if any, by skipping that. But with this instrument going up to higher frequencies, you will want to plan on doing an auto peak and focus observation to correct pointing and focus at the start of any session. And because it is installed at prime focus, it could potentially take about 8 minutes to change receivers depending upon what the other project was before you was doing. So we're saying you should allow for about 20 minutes of overhead per session to be on the safe side. And over time, we'll see whether or not that comes down a little bit, but at least for starters, that's what we would recommend. And as I've said, we recommend that all observers perform pointing and focusing corrections when using this receiver at the start of the session. But just once at the start of the session should be sufficient for most observing conditions. Those are the only real notes I have as far as things that you should be aware of if you plan on proposing to use this receiver. And so I'm happy to answer any questions if there are any and go into any more detail about things.
Thank you so much, Ryan. Do we have anyone that has any questions specifically about the ultra-wideband receiver? If so, you can either raise your hand or put the answer or question in the Q&A. Just a moment. Great. Not seeing any. Thank you, Ryan, very much. Appreciate you sharing that with us. Oh, here there is. Okay, we do have a question. Ryan, do you see this question?
Yeah. Okay,
awesome.
Yeah, so the question is, how does it compare with the Parks ultra-wideband receiver? So it's a very similar design. In fact, we had conversations with them and looked at the work that they did for inspiration. And it covers pretty much the same frequency range. So in that sense, it's similar. The optics of the GBT make it more difficult to lower the spillover temperature. So we can hope, but there's a good chance that we're not going to have quite as good of a TSIS as Parks does, although we'll have a higher gain, obviously, with the larger GBT's collecting area. So that's probably the most straightforward commissioning. I can't quote you on the numbers just yet because, like I said, we're still kind of iterating on the engineering to try and bring that system temperature number down as low as possible. But yeah, same frequency range, very similar design, modified optics for the GBT, and so they should be nicely complementary instruments.
Great. Thanks. Okay, great. We'll switch to the next speaker.
All right, so yeah, happy to be kind of talking with you all today. So just wanted to give a quick overview of the sensitivity calculator. So at this point, hopefully you've got some really interesting background on the GBT, and so once you kind of have your idea in mind of what project you want to do, of course the next step is to figure out how much time you want to propose for. So the sensitivity calculator is a tool that we have available at the GBO to help you with that task. And so we're going to just kind of walk through what sensitivity calculator does and how to use it. So hopefully this might be helpful. So we're going to do a demo as well after I've gone through the slides. So first of all, what is the sensitivity calculator? So it's essentially just a user-friendly way of helping observers estimate the time they need to spend on source, depending on the sensitivity level that they want for the source that they're wanting to look at. So just a very important note, this is not the total time request. So in addition to the sensitivity calculator output, you also need to add overhead time. Or if you want to make a map, then you'll need to plug in your results from the sensitivity calculator into the mapping calculator, which I believe Pedro is going to be talking about next. So that's so sensitivity calculator is not kind of the solution to everything, but it's a very helpful tool to inform what you want to put in your kind of proposal. So one kind of really helpful thing to note is that if you kind of go through the process of doing your sensitivity calculations, you'll have the option to kind of save the output from that, which has a lot of details that are very useful. And we really like to ask that you include the calculation results from the sensitivity calculator in the technical justification of your proposal. That just makes it a lot easier for technical reviewers to verify that your kind of calculations of how much time you need are correct and kind of avoid any potential hangups in the technical review stage. So that's really helpful if you can do that. So here are a few links on how to get to the sensitivity calculator and documentation for it. This is the user's guide. It's extremely helpful. It'll give a lot more detail on kind of the things that we're going to talk about in an overview style today.
Hey, Ellie, I'm just gonna, I think your Zoom controls are at the top. We're seeing a black box kind of there at the top. I don't know if, that makes it worse. Oh, that's good. Great. Okay, excellent. Good. Thanks.
No problem. Sorry about that. Yeah, so let's kind of moving on to the next slide. So just some general information you want to have together before you kind of use the sensitivity calculator. Of course, you want to know what science you're wanting to do, what you want your observation to look like before you start plugging stuff into the calculator. So you'll want, of course, to know, first of all, what sensitivity do you want to achieve? That's important. The other thing that you want to know is what kind of unit of sensitivity are you wanting to use? So there are several different options here. Flux density, antenna temperature, etc. We'll go through each of those here in just a minute. So other information that you'll want to have at your fingertips is what backend do you want to use, what receiver do you want. So of course, the receiver is determined by what frequency you want to observe at. You also want to indicate what bandwidth you want to use. So what size of frequency range you want to use for your observation. You also want to indicate what switching mode you want to use. Of course, Emily explained those a little bit ago. In the demo, I'll show you what switching modes are available for each kind of configuration that we'll be looking at. So the other thing that you'll want to put in is the center frequency that you want to look at, and that could be, the rest frequency of a particular spectral line that you want to look at, or just an arbitrary center frequency depending on kind of what you're hoping to do. So you'll also want to include Doppler corrections and information about velocity, background contributions, and elevation limits. So we'll talk about all this in a little bit more detail when we get to the demo part, because I think it's easier to see how it all fits together. Kind of the last bit is, of course, data reduction information. So basically talking about how you want to average your data, what kind of velocity and frequency resolution you ultimately want to see. And so that's not necessarily the same as the kind of frequency resolution that you observe with, because ideally you want to do smoothing in your post-processing, and that's what you'll kind of plug into your calculator, I believe. So next thing here, we'll just kind of go through the difference between the different units for sensitivity. So first, kind of the most universal, at least as far as I've seen, unit is flux density. So in the sensitivity calculator, this is measured in millijanskis. And so this kind of unit, of course, we're measuring flux as if measured from above the Earth's atmosphere. Now, antenna temperature, on the other hand, is measured from below the Earth's atmosphere. This is a bit different from flux density, and in this case, we're kind of saying what, basically, if we were to replace the receiver of the telescope with a resistor, the power that we would be seeing from the receiver would, yeah, so basically, if we were to replace the receiver with a resistor, that resistor were heated up to a certain temperature, then it would produce the same power as we're seeing with the antenna. I'm probably kind of bumbled that explanation, but yeah, if you have questions at the end, ask me and I'll try and say it more clearly. Yeah, so radiation temperature is similar to antenna temperature, but it's measured from above the Earth's atmosphere and defined for sources of any size. Main beam temperature, on the other hand, is again similar to radiation temperature, but in this case, we're assuming that sources, you're looking at an extended source that's actually extended enough to fill your beam. So forward antenna temperature, in this case, you're measuring antenna power in the forward on sky direction, and you are correcting for atmosphere. So this is mostly used for Argus observations, and this is similar to antenna temperature, just with some differences in how it deals with spillover. Yeah, so that's kind of summary there. So let's talk a little bit about Mustang 2. So of course, Emily is our expert on Mustang 2. So if you have more detailed questions, she is the person for you to talk to. We also have these great resources here to compute sensitivities and integration time, which have pretty much just a lot of really great tips and information on how to do the calculations for Mustang, because we can't, Mustang 2 is not necessarily included in the sensitivity calculator because it has some more kind of intricacies to it that you just have to take into account. Hopefully I'm getting that right, Emily. Correct me if not. Yeah, so that's so that should be pretty much it for the slide portion of the talk. So next up, we're going to actually look at the calculator itself, go through a quick demo, and show you how to do it. And we're going to give it a minute. Oh, yeah, so I have this right here. Okay, so can you see the sensitivity calculator on my screen?
Yes, we can.
Excellent. Okay, great. So we're just going to kind of walk through each stage here. So of course, we've already talked about the differences between each of these sensitivity units. So one thing I'd like to point out here is there are two ways to use the calculator. You can either derive the observing time you need from the sensitivity you want to achieve, or you can derive it backwards. So figure out what sensitivity you'll get given an observing time. So if you know for some reason that you only have this much time to observe and you just want to see how sensitive are you going to get, you can click this. But for this demo, we're going to go with observing time from desired sensitivity, because probably in most cases, that's what you're going to want to know. So again, here are our sensitivity units. For this demo, we are going to select our main beam temperature. And we're going to say, so right here is where you can put in what sensitivity you want. Of course, that's 1 sigma. Gives you the 1 sigma value. So we're going to put 10 in here with the understanding this means 10 millikelvins mean temperature. So we can go on a bit further down. The next thing that we'll be asked about is our hardware information. So for backend, we have 3 options here. These are not all of the backends that are present at the GBO, but these are kind of the ones that are most commonly used. The others are mostly kind of privately used backends, and if you want to use them, you have to have a special kind of arrangement with the people who designed it, built it, or installed it. So Caltech Continuum backend is only for the KA receiver. It allows you, of course, to do continuum observing. But you can see that when we click the CCB, all these fields are kind of filled in and grayed out. So we're only allowed to choose these options. So if you're wanting to do continuum observing with KA, that's an option. We also have the GBT digital continuum receiver, or DCR, which is kind of an older continuum backend on site. So that's another choice. And then we have Vegas, versatile green bank astronomical spectrometer. And this is our kind of most used backend. We can do pulsar observing, spectral line observing, and continuum observing with Vegas. So just a quick note about continuum observing. If that's something that you're interested in doing, it's really important to work closely with green bank staff to make sure that you kind of design the project in a way that's feasible, just because there's a lot of kind of details that need to be figured out with that. So yeah, just generally a good idea to maintain close contact with someone here if you're wanting to do that. So of course with Vegas, we can then choose what mode of observing we want. We can either choose spectral line or pulsar. For this demo, we're going to go with spectral line. And receiver, we can choose from the list of all the receivers that are possible, or that we have here at the GBO. Of course, there's not a guarantee that every one of these will be up during each semester. Some of them are not often used, but yeah, of course, you can propose to use whichever receiver you want, and just kind of bear in mind that some of them are harder to get time on than others. So we're going to choose KFPA for our demonstration here. So now we can actually choose the number of beams that we want to observe with. So it really depends on which receiver you're using, how many beams you can choose. So for KFPA, that has 7 beams, so you can choose kind of any of these configurations. But I'm going to show you kind of some other examples. If you choose KU, for example, you can only choose 1 or 2, because it's a dual beam receiver. And if you choose something like L-band, for example, it gets grayed out because L-band only has 1 beam. So we're going to go back to KFPA though, and we're going to choose 7 beams. We're just going to use all the beams. So polarization here, we have 2 choices, dual or full. If you choose dual, you'll get kind of your left and your right polarization, hand polarization, or your X and Y polarization. If you want full Stokes, you should choose full. But for this time, we're just going to choose dual. So this lets you choose kind of your bandwidth, the range of frequencies you want to observe. So in this case, we're going to go with 850, so we're going to get a nice wide bandwidth. So number of spectral windows here, since we've chosen 7 beams, we can only use 1 spectral window. If we were to choose 1 beam, then we could go up to 4. But again, we're going to stick with 7. So now that we've kind of chosen all these other values, we can move on to our switching mode. So position switching is one option. We can also choose in-band frequency switching or out-of-band frequency switching. So I believe Emily kind of explained how frequency switching works. So the difference between in-band frequency switching and out-of-band frequency switching is that if you're doing in-band switching, your target frequency, so the frequency you actually want to look at, stays in the band, so you're still getting science data, even when you're on your reference frequency. But when you're doing out-of-band frequency switching, your target frequency goes out of the band, so you're no longer collecting science data. So what that ultimately means is that N-band frequency switching is a lot more efficient because you're collecting science data all the time, even when you're kind of observing with a reference frequency. So one other thing I'd like to do really quickly is show you that there are actually more options you can look at for switching mode if you choose 2 beams instead of 7. So you can see we've got a couple more options added in. So if we're using 2 beams, we can nod between beams, or we can do subreflector nodding. So nodding in general just means, like as Emily described, just moving the telescope so that the object goes from being centered in one beam to the other, and the non-target, the beam that's not on your target, is collecting reference data. Subreflector nodding, of course, instead of moving a telescope, means you're moving the subreflector to do basically the same thing. But we're going to go back to 7 beams, and we're going to do in-band frequency switching. So yeah, so next we would like to put in our source information. So I want to specify our frequency in either topocentric frame or rest frame. So rest frame, of course, is, so let's say you're wanting to look at neutral hydrogen. If you selected rest frame, you just put in kind of the lab determined frequency of neutral hydrogen, just, you know, kind of the equivalent of that. Topocentric frame corrects for Earth's motion. So yeah, so normally the default is rest frame, so we'll just stick with that. For this observation, we're just going to go with 24,000 megahertz or 24 gigahertz. Yeah. So Doppler corrections, this is also a good thing to talk about. So this is how you're correcting your source's frequency for, of course, relative motion between the observer, us, and the source. So there are a couple of options here. We have optical, but we have radio, optical, and redshift. So optical Doppler corrections are basically just an approximation of the redshift or relativistic Doppler correction. So optical works good for sources that are moving kind of below about 10% speed of light or so. Redshift, which is similar, basically relativistic Doppler correction, works pretty much for any source. Radio, on the other hand, is not particularly recommended because there's some issues with how that's defined. Unless you have a very specific reason for using radio, it's best to go with optical or redshift. So source velocity here, we can put in, if we know the source's velocity, we can kind of enter that right here in kilometers per second. We're going to leave that at 0. So we're pretending for the purposes of this demo that we're wanting to look towards the galactic center, and that's kind of roughly 0. So we'll just leave that alone. Source diameter, we'll leave that alone. Of course, we can't change it here. So the next thing to look at is source contribution correction. So what does this mean? Well, basically, if you're looking at a direction in the sky, you want to know if you need to kind of correct for the background, things like that. So you can either do a user estimated correction and enter it right here, or you can do internal galactic model, in which case you need to specify the approximate right ascension so it can kind of do the correction for you. We're just going to do a user estimated correction, leave it at 0 for now. So next thing on the list here is we have source declination in degrees. So why do we need to give the sensitivity calculator our declination? Well, that actually allows the calculator to determine the minimum acceptable elevation that we can put in depending on our source. So let's put in our correct declination for the galactic center. It's about -28 degrees. So the recommended minimum elevation in general is 20 degrees, but I'm going to leave it alone, and I'm actually going to click update results here to show you something really quick. So what we see here is that minimum elevation is below the suggested minimum of 12 degrees. So our declination allows it to calculate this value. So if we move it to 12 degrees, then that error goes away. All right, so the next thing that we come to here is data reduction. So the first question, of course, is the ratio of observing time spent on source or on frequency, compared to that spent on a reference position or reference frequency. So if you're spending equal time on your source and on your reference, then of course that value is 1. If you're spending twice as long on your source than you are on your reference, that value is 2, etc. We're going to leave it at 1. So we're just going to assume that we're going to spend the same amount of time on our source as we are on our reference. Or in our case, the same amount of time on frequency as we are off frequency, on reference frequency. So another question here. So in data reduction, you have the option to average multiple reference observations in order to improve the noise. So enter the number of reference observations that will be averaged together. So so basically, if you want to average more than one of your reference observations together, you indicate the number there. Pretty self-explanatory. So here are some other options. So if you aren't really interested in looking at the difference between polarizations and you just want to average them together to kind of improve your signal to noise a little bit, you can leave this checked. If you want to difference your signal and reference observations, which for spectral line observing you usually do, then you leave this checked. So the last thing here is smoothing. So this is, as we talked about, this gives you your kind of velocity resolution that you ultimately hope to achieve. So if you want to look at your kind of spectra with a resolution of 1 kilometer per second, you leave this alone, or you can edit it to say, okay, I want 0.7, I want 5, whatever. So we're going to leave it at 1. So now that we've kind of walked through that process, we can go ahead and update our results and see what happens. Yeah, so 10. Right, so that, so you can see over here our results. We can look at kind of the derived total observing time at 764 seconds, which is slightly different than I expected, but that's okay. Let's try and update our, yeah, so that's what I expected. Okay, so if you put your minimum elevation at 20 degrees, this changes a little bit. The time went down. So of course a bit harder to observe at lower elevations due to refraction and other effects. So so our total observing time here is 628 seconds. So this tells us the amount of time that we spend on our signal frequency, so our target frequency, of course half of the total value, and this gives us the time on the reference frequency. So you can scroll through here and see all kinds of information about kind of the calculation, about your setup, and if you'd like kind of more detail about each of these fields, the user's guide for the calculator has a lot of great information. You can also click, if you want to change how you display this, you can click over here and it shows it as a grid, which is very handy. So the other thing you can do here is choose to save this to a file. So I'm going to go ahead and open it, and what that does, pull it over here, it kind of prints all this out into a file, and you can of course select all, copy, and then paste that into your proposal. So hopefully pretty straightforward process. Yeah, let me double check if I've missed anything. So I did just want to make a quick note about 1/f noise. So if you're wanting to do continuum observing, and you kind of put in a configuration and it spits out an error about 1/f noise, then you do want to pay attention to that, and make sure that you talk it over with someone who's an expert on continuum observing with the GBT, or just make sure that you kind of take care of that, because you don't want to kind of submit a proposal for continuum observation and have it be rejected because it's not been checked out technically. Yeah, just a note there. Yeah, so one final thing I'll point out is pulsar observing. So you can choose spectral line or pulsar. If you choose pulsar, There are some additional fields here to choose your duty cycle, which is just the percent of the pulsar's period. So yeah, it's basically the pulse width over the pulsar period. And the effective bandwidth is kind of the bandwidth you would actually expect to see with your given setup, which could be, of course, affected by RFI and all kinds of other things. So yeah, so hopefully that's, I think that should cover it. If you have any questions or corrections for other panelists have corrections to anything that has been said here, then yeah, I'm all ears. Thanks.
Thanks, Ellie. Thanks very much. So we have some time for some questions. We also have a scientist online as well to help us with questions. So if you have any questions, feel free to raise your hand, put it in the Q&A, or just directly message it to us. Go ahead, Pedro. Pedro's going to tell us about the GBT mapping calculator.
Thanks, Emily. Hello, everyone. I'm Pedro Salas, and like Emily said, I'm going to tell you a bit about mapping with the GBT. So the way I'm going to do this is, first I'm just going to go over some basic concepts, and then we'll end up with an example of how to use what's known as the GBT mapping calculator, which is what we recommend you use if you have a mapping project. Please use the mapping calculator. So in general, what is mapping? Well, if you want to know how the spatial distribution of something, say the emission of the recombination line emission over the galactic plane, then you would have to map with a telescope like the GBT. Right, by default, the GBT is only if you only point in one direction, it's gonna give you information about that specific area, an area roughly the size of the telescope beam. So if you wanna have information of more than this one pixel, so to say, you would need to map. In general, when you should map, it's going to depend a lot on your science case. There's no unique answer. And that's a bit what this cartoon on the left tries to show. Some of the questions you might be asking yourself when deciding if you should map or not. And as a rule of thumb, the half power beam width of the GBT, it's roughly 12.3 arc minutes divided by the frequency in gigahertz, right? So if you were observing at 1.4 gigahertz, the beam width would be roughly 10 arc minutes. So that means that if you point in one direction using the L-band receiver, you're going to be gathering information about this 10 arc minute area. So once you have decided if you should map or not, then you will go to use the mapping calculator, and that's going to tell you how long it will take you to make a map given some inputs. And we're going to go through those inputs in a minute. But in general, what you want to know before going into the mapping calculator is how long you need to integrate per beam. So that would be the output from the sensitivity calculator, and how large an area you want to map. And once you know those two things and which frequency you're going to be observing at, you can then determine how long it's going to take you to complete a map. Some specifics about mapping with the GBT. Well, one of the things that we should consider are which are the kinds of maps available to be made with the GBT. And the first one is on-the-fly mapping using a rectangular mapping a rectangular area. This is a very commonly used method because it gives uniform sensitivity across the map. And It allows you to continuously collect data as the telescope moves, so it provides a good image fidelity, especially if you're using a telescope like the GBT with its very clean beam. And more specifically, for this method, you can choose to map in two directions. You can map along the along the right ascension direction. That's what's shown here in this figure. And the telescope would do a map following the white arrows along your source. So one can specify how big the rectangle is one wants to map, and how much to separate between the different rows on the map. Alternatively, one could map in the orthogonal direction. In this case, would be in the declination direction, in which case the map would go up and down and up, and so on, and move to the side. And while using on-the-fly mapping, you can combine this with position switching. So, for example, every so many rows, you can stop the mapping and go observe a reference position to calibrate your data. Or you can use frequency switching as your mapping, so you're continuously switching between on frequency and your off frequency, so you can calibrate all your integrations using that. Additionally, if you're mapping an object which is smaller than the area if your area of interest is smaller than the full map you're covering, you could alternatively use the regions around the edges of the map to calibrate your data if you don't expect, say, line emission in the edges of the map. Some of the other mapping patterns that the GBT knows of are this daisy mapping, in which case the telescope will draw a trajectory following these petals, and it will slightly shift after it completes each combination of 3 petals. It shifts a bit, so so it ends up covering something of a circular area. And as you can see here, the sampling is much more dense in the center than at the edges of the circle. So this mapping method is recommended, for example, if you are interested in a small object near the center of the field. You could think about using daisy mapping. But if you want to have uniform sensitivity, we would recommend you use the rectangular mapping. And there's a third alternative, that's point rectangle mapping, which is very similar to the on-the-fly rectangular mapping. But in this case, instead of continuously acquiring data as the telescope is slewing, here you would only acquire data at specific positions which you specify beforehand. So the telescope would start here, for example, dwell on this position a couple of however long you need to integrate, and then it would move to the next position and repeat the same, integrate until you reach the amount of time you need for your science goals. As you can see in this example, while the telescope is sitting at one position, it's gonna move a bit, right? We have a very big structure and it's exposed to the elements, so there's gonna be small changes in the pointing, but in general, these changes are much smaller than your beam. So it's usually not something to worry about. So once you know which kind of map you want to do, there are some other considerations that you have to take into account. In particular, depending on the receiver you use, you might be able to map faster. That's one of the reasons why people build multiple pixel receivers or phased array feeds or focal plane arrays, because with these receivers, you have multiple beams on the sky simultaneously. So as you're slewing across the sky, the same position gets observed multiple times. So what does this mean is that then the total time you need to complete to reach a certain sensitivity in your map is a fraction of the time you would need if you had a single beam receiver. In this case, we're showing the disposition of the beams in the K-band focal plane array, where you have 7 beams. And in this particular case, say for example, the sensitivity calculator says you need a time of 700 seconds to reach your sensitivity at one position. If you're mapping an area that's larger than the footprint of the KFPA, then you can take that time and divide it by 7, because we have 7 beams, and that would be the time you need per beam to reach the same sensitivity, right? Just because we're mapping the same area with 7 different beams. So that's something to keep in mind. The mapping calculator will not incorporate this information per se. It's something you have to input by hand. And of course, depending on the type of experiment you're doing and the calibration method you choose to use, be it position switching or frequency switching, make sure you use the correct time when as input to the mapping calculator. For example, if you make your calculations in the sensitivity, well, this applies very much for position switching mainly. If you're making a map using position switching, the sensitivity calculator will give you a total time which considers the on plus off time for a single position. But when you're mapping, you can basically use the same off position for multiple on positions. So for the mapping calculator, then it's better to use the on source integration time from the sensitivity calculator, and then in your overheads, include an additional time for the off calibration, instead of considering that for each sample you're going to be needing the total time. Then that really makes the total required time longer than what is actually required. Some other things to keep in mind if you're going to be doing mapping observations is how would you handle your data after the fact. And just wanted to mention that there are observatory provided tools that will help you process your mapping data, or any or most of the observations that the GBT can do. 2 of these are GBT IDL and the GBT pipeline. And in particular, the GBT pipeline will work with any receiver which has noise diodes, so that would discard the W band and Argus, but for the rest of the receivers, the GBT pipeline would work. And it's quite convenient because it gives you a fast and quick way of taking your raw mapping data and turning it into an image, a cube, so you can assess the data quality and then modify change the details to improve the image quality. In terms of turning the calibrated data into a cube, there's the GBT Grider, which will do that for you. It's designed to work specifically with GBT data, and in general, all these tools work with single dish FITS files, which is the default data format, the spectral line that we use for spectral line observations. And now I'm gonna switch to using actually the mapping calculator, so we can see what the inputs are and go over this and answer any questions you might have. So I'm gonna stop sharing for a second, and I'm gonna switch to the mapping calculator. Okay. So this is the landing of the mapping calculator. So if you just go to this URL, this is what you would see. And it starts with a brief introduction. And in general, you will see on the left the input values, and then on the right a description of what those input values are, and some suggestions for choices in case you're wondering what you should use. If you're just exploring the possibility, for example, like you have an idea and you want to know how much time would be required to do this idea, you can just use the default values, and those are in general pretty good. So the first thing it's going to ask us is, well, which kind of observation we're going to do. Is it a continuum observation or a spectral line observation? And which calibration mode are we going to be using, total power or frequency switching? We're going to build on Ellie's example, so we're going to choose frequency switching. And for the observing modes, this is quite convenient because it gives you a mode name, but also it tells you the total bandwidth of that mode and the number of channels. So you can have so you can determine roughly what velocity resolution this would correspond to at the frequency you're observing. In this case, we're interested in doing observations at K-band using a velocity resolution of roughly 1 kilometer per second. So most of these modes will be able to deliver that below mode 3, roughly. So we're just gonna pick mode 5, which has a bandwidth of almost 200 megahertz and 66,000 channels. And again, frequency switching, we're gonna say, yes, we wanna use the noise diode, because without the noise diode, then it becomes trickier to calibrate our data. And we're gonna choose to use Doppler tracking using the first LO, the first local oscillator. So then the next question is gonna be, what kind of map would you like to use? And this is where the maps we were describing earlier come into play. So it gives us the option of using the rectangle map, using on-the-fly mapping, on-the-fly Daisy, and the point rectangle map, right? And depending on which one of these maps you choose, some of the options below will be slightly different. Then it will ask us for the frequency of our observations, and this is mainly used to determine what's going to be the beam size of the telescope at the frequency we're observing at. So you want to use a value that, in general, you would want to use the highest frequency of your observations if you're spanning a broad frequency range, because then the map is going to be properly sampled at this higher frequency where the beam is smaller. For this example, since we're interested in narrow band observations, only 200 megahertz at a frequency of 24 gigahertz, we're just going to use the central frequency. And it goes in megahertz, so careful with that. And then it's going to ask us for the integration time per beam we want to use. So from Ellie's example, she determined that the integration time per beam, since we're using frequency switched observations, was roughly 600 seconds. And because we're going to be using the KFPA, which has 7 beams, then we take that time and divide it by 7, which gives us something like 89 seconds per beam. So here we can input that value, and we'll use that, because as we said before, we're going to be observing the same area of the sky with the 7 beams. So the sensitivity per beam, so we can reach the same sensitivity per beam using just a 1/7 of the time. And then it's going to ask us for the map size. So in the case of, and here it's the input is going to change depending on which kind of map you're using. So if you're using an on-the-fly rectangle map, it's going to ask, it's going to use the two first options. Or if you're using a on-the-fly DAISY, it's going to use this third option. So in our case, we are interested, let's say we want to map an area which is 6 by 6 arc minutes. The inputs are in degrees, so that would be only 0.1 times 0.1 degrees. And we can just leave this with the default value because it's going to ignore it since it's an on-the-fly rectangle map. And then it's going to ask us about the details of how we want to map. The first question about the details of the map is how far apart we want to separate the rows or columns of the map. So in the example we were looking at with the image of the Crab Nebula and the trajectory of the telescope in the right ascension direction, this is basically going to tell us how far apart we want those rows to be from each other. And this is going to be a fraction. This is going to be expressed in a fraction of the Nyquist sampling rate. So that means if we leave it at a value of 1, it's going to separate the rows using the Nyquist rate. So lambda over 2 times the diameter of the telescope. And that's by default, that's a good sampling rate if you want to avoid having artifacts in your map. If you want to put your rows closer because you want to have a higher quality map, you can increase this value. And as we see here, it mentions that, for example, values larger than 1.2 are seldom used because then you just get a lot of redundant information. But this can be useful, for example, if you want to map, if you want a very deep map, but then you have problems with the integration time, you can play a bit with these things to fit your whole observation into one block. So we're going to leave that as a default value. And again, it also says that if we use values lower than 1, we would undersample our map. And then when we make an image out of this mapping data, we would end up with a lower quality image, just because we don't have all the information we need. Then the next option is how much to sample along the scanning direction, right? So if the telescope is moving in the right ascension direction, how often to sample along this direction? And this is basically going to be determined by a combination of how fast the telescope is moving, how long the map is, or how wide the map is, and how fast the backend is recording data. So it's there's a few parameters going into that, but in general, it's just a simple calculation. But it's quite handy that the mapping calculator already knows the limitations of the telescope in terms of how fast it can move and how fast it can basically record data. So it will warn us if something is not right when we input these values. I mean, on the next page. So we're going to leave it at a value of 2, which is the default. So to sample, to roughly to sample well enough in the scanning direction that we don't get any funny artifacts in our data. And again, if we choose a larger value, it's going to take longer to get the full map done, but the quality is going to be higher. And if we use a lower value, then we start losing information. So in general, unless you have a very good reason for not choosing the default value, you should, I would recommend you go with that. And then finally, we have the number of switching periods per integration. So that basically is telling us how often to cycle between states in the recording process. So for example, if we're using the noise diodes, this is telling us, well, how many times do we want to fire the noise diodes during an integration? By default, it will select a value of 4, which again is a good compromise between overheads and image fidelity. If you use higher values, you will spend more time switching between these states, and that means that there's more time spent blanking the data that goes into the backend. So you will be effectively having less data. It will take longer to reach the same sensitivity. And if you use a lower value, it will go faster, but the data quality might not be as good. So once we have all these inputs into the mapping calculator, we can go ahead and you can either hit just enter in any of the prompts or hit the submit button, and it will give us the results. So the first thing is it's gonna warn us about Doppler issues with the Doppler tracking. So if the lines are gonna get too broad, it's gonna tell us how broad they're gonna get. In this case, the broadening of the lines is quite small relative to the typical line widths of an ammonia line. So it wouldn't be, so we could, in this case, we could safely ignore this warning, and then it will proceed to repeat some of the information we used as input. So for example, and it's just gonna make it explicit that it's assuming that the telescope is a 100-meter telescope that has, for example, that we select a frequency of 24 gigahertz and the type of map we were using. So this is mainly for debugging purposes, or just to, it's useful also for us when you're writing the proposal to take all this information, so the whole thing, and put it in your proposal. So then we know exactly which input values you used, and we can reproduce your calculations when assessing if the observations are feasible or not. Then it will give some more information, like how broad the beam is going to be at the frequency we're observing, what the wavelength is, how big the mapping area is going to be, a series of things. And then comes the, I would say, what personally I pay more attention to, that is actually how long it's going to take to make this map, right? That's in general what we really want to know when writing a proposal. So in this case, it's going to give us the total time down here. And this is if we were to map along the right ascension direction, right? So it has a total time of 3.4 hours, roughly, which we would have to round to 3.5 hours, right? Because we have to, the telescope is scheduled in 15-minute intervals. Up here, it actually tells us what the time for the map is, and then it tries to estimate how much of overhead you would have for the given configuration that you're using. So it adds these two things together and gives us then the total time. And then it gives more specific details, like how fast the telescope is going to be moving and how many accelerations per minute are going to be happening. And if any of these values was above what the telescope can tolerate, it would warn us about that. And then, very conveniently, also the mapping calculator tells us what would be the commands we will need to use in our scheduling blocks to actually carry out these observations. So it will give us this asterisk directive where we see that the command is, okay, the right ascension longitude map, where one specifies the source name and then the size of the map, well, the width of the map, the height of the map, and then how much to space the rows in the map. Then it tells us how long it's gonna take to complete one row of the map. So just one slew along, in this case, one horizontal slew. And then it also tells us how many rows it's gonna have and where to start and when to stop, which can be useful, for example, if you have to stop your observation in the middle of a map, then you can resume it the next time you get on the telescope by changing the start value. And it will also give us what we should input in the configuration tool as our integration time and the switching period. And as you can see, this is just 1/4 of the integration time. So that's that last value we're talking about, that 4. And then it ends up giving us also the same, but if we were scanning in the orthogonal direction, right? So in this case, since it's just a square map, it makes no difference. So the results are exactly the same, except that the asterisk directive, now it's different. And particularly the spacing between columns, now in this case, it's specified slightly different than the spacing between rows. Just notice that this value here appears as the second argument, and in this case as the third argument. Yeah. And in general, if there was any issues with the setup we selected, it would warn us down here. So we can go back, for example, and let's say we want to map a very, very strong and bright line. So let's say we only need 5 seconds per beam to accomplish your science goal. What would happen? And it would tell us, for example, warning, due to the limitations of how fast one can sample or move, the actual time per beam differs significantly from what was requested. So we wanted 5 seconds per beam, but it's telling us that it would deliver only, that it would deliver more than that, 19 seconds per beam, because the telescope, in this case, I'm not sure if it's because it's moving too fast or the sampling. I would guess it cannot sample as fast as needed. And yeah, you can play a bit with this and see what happens. Like if we were to make this super small, I think we would hit an acceleration. Yes, so then we would get 6 accelerations per minute. We cannot go above 2, so it would issue a different warning on top of the one we had before. So if you were in one of these situations, you would have to go back again and change the inputs so that there's no errors, right? So it's still the super small map, but now we tell it we want 100 seconds per beam. So now the telescope will effectively move slower, so it's not going to accelerate as fast, and we're going to get the time per beam we actually want. And I think that's all I had for today about the mapping calculator. So please remember, if you are submitting a proposal, use that, and you want a map, please just take this whole thing and paste it into your technical justification. That's going to help us greatly, and we would really appreciate it if you do that. Thank you.
Great. Thanks so much, Pedro. Are there any questions about mapping? As always, you can put it in the chat. You can put it in the Q&A or raise your hand. Okay, hearing no questions. Thank you very much, Pedro and Jesse. Please take it away for our last section of this workshop.
Okay, perfect. Thank you very much, Emily. Hi, everyone. So today I'll be talking about the proposal submission tool, which is where you're going to actually apply all of this information. So first things first, once you have thought about the science that you want to accomplish with the GBT, you can submit your proposal through a specific proposal submission tool, which is available up on the mynrao.edu website. The links are available throughout these slides, as well as on the call for proposals, and in addition to the proposal planning workshop website. And so this tool is used not only actually for the GBT, but also other telescopes like the VLA, VLBA, and the GMVA. And so depending on what telescope you are interested in, that'll vary the information that you have to submit into the PST. So in this case, we are specifically just talking about GBT. So once you've logged in, up on the top left, there are a number of tabs. You can select the proposals tab and choose a new proposal. In this example here, you can see that this person has submitted many past proposals, and these all show up for you. On the very left, you have a options window. You can choose whether or not you only want to see submitted proposals or draft proposals, if you like to keep several drafts created for whatever time you might need them. And if you want to start a new one, you can choose the top right corner, or you can click on any of the past proposals to look at them. So once you create a new proposal, you then have to select which telescope you want to use. In our case, that is the GBT. And then this is the page that you will see. So it's broken down, as you can see on the left-hand column, into several different sections. There's general, authors, sections for the science and the technical justifications, and then the setup of your sources, your resources, and your sessions. And we'll actually be looking in real time at a proposal in just a moment. So at that point, I can go through all of these details for you. But generally speaking, these are the components that you need to have in a proposal. On the main page, you need a title and an abstract. You need information about the type of proposal and the science that you're going to be carrying out with it. And information like if it's a joint proposal, whether or not it's related to a previous submission of a proposal. Then you need to add all author information. These all need to be NRAO registered users in order for you to find their name and add them to the proposal. Next, we have the science justification. So this is a separate document created in your favorite Word editor, which has to be, for most proposals, within 4 pages, including both primary text, figures, tables, and references. Though you do get a larger submission size for specific large proposals. The technical justification consists of 9 text boxes with questions that need to be addressed. This is where you're going to input the sensitivity calculator details and the mapping calculator output as well. And then lastly, you have these interlink sections where you get to list what your sources are, giving their RA and DEC, velocity, that basic information, giving them labels. Then you can set up your resources. So this is actually the instrument information that you wish to be using, the receiver, its bandwidth, etc. And then finally in the sessions, you're actually taking those sources, taking those resources and combining them in order to set up specific observing sessions that will address your overall proposal request. All right, so now that we have all of that, let's stop this share and move over to the observing proposal. All right, so you're going to go to mynrao.edu and you're going to want to log in. Once you're here, up on the top left, you can go to the Proposals tab and you can see all the proposals that you've submitted, but up on the top right, you can select a new proposal. For us, we want to use the GBT, not any of these other telescopes. And then again, up in the top right, there's a box that you can hit Create, and that will get you started on your observing proposal. So you're started out here on the general page. In the top right, you have a status of your proposal. It lists the date that this was created and most recently modified. And once you've actually entered the information, it will tell you the total time that you're requesting. So if we use, again, that top right button and edit, we can start inputting information. Now, every good proposal needs a good and catchy title. And since we are interested in ammonia mapping of some theoretical region like the galactic center, we need an interesting start for that title as well. Every astronomer wants a cool, catchy name. So we're going to go with the generic observation, mapping ammonia in the galactic center, also known as Go Magic. So our proposal is going to be a regular. We're not asking for an overly large amount of time. This isn't triggered. And we're not asking specifically for director's discretionary time. This is just a standard proposal. We do not have a sponsor for this one in particular, but if you did have one, for instance, you're part of the Nanograv collaboration or through West Virginia University, then you need to include that information here. The scientific category. So this is useful for when your proposal gets to be reviewed, so that proposals can be separated out into different types, so that reviewers with knowledge or general knowledge of your field of interest can properly review it. So in this case, we're not looking at AGN. It's definitely not extragalactic structure. It's the galactic structure. So let's say galaxies. We're looking at a particular galaxy, or rather the interstellar medium. We're looking at gas between us and the galactic center. Then you want to include an abstract. You can see that there is a word count limit. So let's go with, this is my abstract. It is at least 10 words long. All right, you click off and you can see it's keeping track of the number of words that you've used. Perfect. We're above that limit. All right, now you have to enter the information. If this were a joint proposal as part of the VLA or another observatory, such as Hubble or soon to be JWST, Chandra, etc., you can include that information here. And then we need to include information about what type of observing. So here we want to look at ammonia. So we're doing spectroscopy and, well, we're definitely doing on-the-fly mapping. And if there are any other categories that are relevant to your proposal, go ahead and include those as well. We are not going to be using this for a dissertation. And this is not related to any previous proposals, so we don't have to worry about those sections. So now that this is all filled out, we can go again up to the top right and press save. Great, now we've got all that information included. Next, we want to go into the authors section. And you can see that since I'm the one creating this proposal, my name has already been entered. But let's say I want to add somebody else, such as Pedro Salas. So I type his name in and do a search. You can also search for just a part of their name or their email address. And sure enough, Pedro shows up. Great. So I can click on his, select his name and press save. And he is now a member of my proposal. You can do this for however many members you want. You can also rearrange the order, but generally, this is all good. So now we can go into our science justification section. This is, at least for me, usually one of the last sections that I'm filling out, mainly because this is completed elsewhere on my computer using LaTeX. And once that's done, I can create the PDF and I can upload it here. So I would go to use this add button and select that PDF format. I should point out as well that we only accept PDF or .txt files with specific limitations on the fonts that you use, the page numbers, as well as the total file size. So please be aware of these things before you submit them. as they will detract from the overall value of your proposal. Then relatedly, we have the technical justification section. So these are the series of 9 text boxes that I mentioned before. Unlike the science justification, you can just enter the text directly here on the right column, and there are no specific word length limitations. However, I don't think we want to read and review a proposal with several pages worth of text here in this technical justification. So simply provide enough information to answer the question. So you can go down these and not all of them will apply to you. So first and foremost, it asks for the dates and times of any fixed observations as part of our proposal. Well, we're mapping ammonia at the Galactic Center. We don't have any specific time requirements here. So I'm just going to say not applicable. That's perfectly okay. Then we have to justify the resources that we're requesting, the observing mode and all of those values. Specifically, it mentions that if the sensitivity calculator has been used, please include that information. If not used, then include any equations that you have used in order to determine that sensitivity information. So here we can hop over to the sensitivity calculator, which we've already filled out and gotten our total observing time. And we can just go through and copy all of this text. Come back over here, and once we've answered the questions that it is asked through a paragraph explaining it, we can go down a few lines and just paste all that information in there. If you want, we can increase the size of this box so that you can see what's actually entered there, but it's going to be quite long. All right, and then for any mapping calculations that are needed, we want to enter that information here. So once again, we can go to the mapping calculator and we can select these values here. This is useful not only for the reviewers of your proposal, so they can verify any results, any time requests that you specifically request by re-entering these values into the sensitivity or mapping calculator. But it's actually also useful for you because let's say you completely forgot what you had originally entered into your mapping calculator. It's time for you to observe. You have to write your scripts. Oh man, there's this really handy information in the mapping calculator. Well, thankfully, all of that information was just copied and pasted. And as long as you have access to your proposal, you can go back in, you can find that asterisk directive for creating an RA long map and copy and paste that right into a script. And then the last few, discuss RFI impact. No matter what you're observing, there is a risk of RFI. So you need to at least address that. For me, I tend to observe in the higher frequency with the GBT using Argus, where there isn't currently any major RFI. I've checked this. I'm familiar with interference frequencies in the area, so I can say as much. However, for a lot of lower frequencies, there is a lot of RFI. You need to be prepared to explain how you're going to handle navigating that RFI, removing it from your data, or specifically looking at lines where it is RFI free. And then you need to discuss the overhead time. So this is another paragraph where you need to mention not only the time that is given by the mapping calculator, but any information for changing of receivers, both at the beginning of your observations, when someone else was just using a previous one, or if you are using multiple receivers, multiple instruments, you need to account for that time. The slew time, pointing and focusing, and then for higher frequency observations, such as Argus, W-band, you need to account for the time spent performing an auto-OOF. So all of that information should be entered into a paragraph or two here. And then for joint proposals, you need to discuss how the two observations, the two telescopes are going to be working together using that data. If you have any particularly novel observing techniques or data reduction methods that you're going to be utilizing, we want to know about that. That can affect the ranking of your proposal. For pulsar observations, you should include information about the pulsar. And finally, if you have very specific needs for a minimum or a maximum LST at which you're going to be observing, you can discuss that here. So once we have completed that, we can go up to the top and save. And at any point, if you want to leave one page, come back later, you can always save it and continue to re-enter information before you submit. All right, the home stretch. We need to add in our sources. So you got a lot of buttons here at the top now. You can convert, export, import, copy a source from another proposal, or what we would like to do, start completely fresh with a brand new source group. First, ask for a title. This can be whatever you want it to be. I'm just going to call it our source, since we just have the one. All right, we press save. And now that we've got our grouping, we can populate it with sources. In this case, we just need one. And that is going to be Sag A star. We're going to look right towards the galactic center. We can manually enter information like it's RA and DEC, or we can go up here and search NED. Oops. I think it needs that distinction there. No, it's just very angry with me. Oh, okay. In the past, I have gotten this to work. I don't know why it's grumpy with us. All right. In this case, I am just going to go with a favorite of mine, NGC 7293. Okay, there we go. So you can see that it has populated all the basic information. It's RA and DEC, its velocity, and its reference frame. Perfect. So now we can save this. And if we had multiple sources that we wanted to include, we can add them here. However, it is also important to keep in mind that when you will be selecting when you're creating your sessions, you'll be selecting a source group. And that is not necessarily going to be all of your sources. You don't want to observe, you don't want to map 3 galaxies all in one individual session because you have a limit on time. So if you have too many sources that are very different from each other in the plane of the sky and so forth, then you want to break those out into separate source groups. All right, now we can set up our resources. We can choose to copy, or we can create our own. So let's create our resource group. Let's call that ammonia resource. All right, let's save the group. And now we can add individual resources here. So we can call this whatever we want. And then we select the information we need. So we're going to be observing with KFPA. We're going to be using the Vegas backend. We're going to be doing a spectral line, not a continuum observation, using 7. There it goes, 7 of the KFPA's beams. And you can see those are populated through the 8 individual spectrometers that we have available. So specifically, we'll be using 7 of them. And here it is where we can submit information like the mode that we'll be using. So as Pedro was setting up the mapping, he selected mode 5. And so we have information like the bandwidth that has been filled in for us. Now, the rest frequency, also very important. Also important to note that this time it is in gigahertz, not in megahertz. So you don't want to get those mixed up. The spectral resolution for this particular setup has been filled in for us, and it assumes a base integration time as well as a data rate for the spectrometer. In this case, we want to use a different integration time. So if we came back here and we went and took a look, we can see that the time that we submitted, I believe, was around 90 seconds. So we'll want to enter that here. Oops. I may have misremembered. So I'll just go with this here. All right, and as you can see, the data rate spectrometer changes to fit with the values that you've inserted. All right. Let's try and submit. Nope, there's an error with the frequency. What are you having an issue with? All right, not important for right now. I'm just going to cancel, but generally you'd want to save that resource. All right, once you have those correctly filled out, we can go to sessions and actually create a new session. You can give it a session name. And then you want to figure out the number of sessions. So here's where you actually need to think about your time request. In this case, we determined through the mapping calculator that we only need about 3.5 hours in order to complete our map. Now that's not including any overheads. So if we assumed, let's say, a half an hour worth of overheads, this is KFPA, not unreasonable. In a real proposal, we'd want to actually think about it and compute those values more carefully. But I know that it's definitely going to be less than 6 hours, which is generally an upper limit to a individual session request. So if this was a full 16-hour map that we wanted to make, we're not going to be able to do that in just one session, because on the DSS, which schedules each of these observing sessions, it's going to try and find a time where the weather and the receivers are correct, where there's a 16-hour window, and that is almost unlikely to ever exist. So your project would never get scheduled. That's why you need to keep it to much lower values. So if it was a 16-hour session, a 16-hour observation, including all of the overheads and stuff, then we might want to break it up into, let's say, 3 different sessions. Or if you want to keep the numbers nice and neat, 4 sessions, each of 4 hours. In our case, it's 3.5 hours plus a half-hour overhead. So that's a 4-hour session, and we only need 1 of them. If we were needing to do specific observations of a source over consecutive days, then you can specify the day range. You can determine a minimum and a maximum LST if that's important to you. And we can also enter our desired minimum elevation here. If you have any particular constraints or comments to your scheduling parameters, you can include that. Then if we had multiple source groups, we can select those here. If we had filled out the resources, there would be one here. And we now have everything that we need. We can press the save button. All right, and with all of that gone through, at the very end here is disposition letter. There is currently nothing available. That is because we haven't submitted this and it has not been reviewed. However, you can always go back. Okay, it's being very upset with me today. I'm not sure why that is. All right, so you can always just press the back arrow and you can get back into your main proposal. Going back up to the top, you can see that we've filled out a lot of this information. If we had submitted a completed session, it would update the total time with that information. And it also keeps track, as I mentioned, when you submitted and so on. So now that we have all of this done, we would then want to go up to the top left here and press the validate button. So this will go through and check if we have everything that we need for our proposal. Clearly, we do not have a submission-worthy proposal. So we're definitely going to need to go back and edit it. But once you have everything completed, you can then go up to the submit button. Submissions will also perform a validation. However, it's often good just to be checking. You can always print out a copy, but the proposal itself will be here and available under your proposals tab. So if I were to leave, log out, and come back in, you can see that all of this information has been saved. And I can just choose to go back to my proposal and continue to edit it as needed. All right, now let's quickly switch back over to the presentation. So now that you have the general overview of how you think up a proposal, how you write down your proposal and submit it, these are the other details that you need to keep in mind when you're creating this. So as Emily had initially mentioned, there are specific components to the type of proposal that you request, whether it be a large or simply a regular proposal. And so the number of hours that you need is going to determine those. For large proposals, you also will need to consider including information like how you're going to process and reduce all of the data that you collect. And so that should be included in your science justification upload. The other types are triggered proposals and the director's discretionary time. Again, so these are for specific situations. If you have a proposal that is planned for a certain event, certain time period, you can choose a triggered setup. Or if you suddenly need to make an observation that is out of the normal proposal submitting time, you can create a director's discretionary time proposal whenever during a semester, and you submit it. It goes through a similar review process, but much more quickly. So this can be important when you need to do some exploratory observations of just a couple of hours for a related project. If you need to, if you're connected with a receiver and you need to do some testing, need to take some data in order to verify its abilities, or a target of opportunity, a specific phenomenon has occurred, and you want to get observations while it still is in the sky. Now, for the proposal review process, there are, of course, a variety of proposal types. There are a handful every year that are standout, great proposals, almost guaranteed to be selected. And there are also ones that were not given a great deal of thought and are generally considered fairly poor. However, the vast majority of the proposals, so this is a few hundred every review period, are wonderful proposals that are very different or unique from each other, but not inherently better than the vast majority of the others that have been submitted. So that makes selecting the proposals very difficult. So there are some things that you can keep in mind when writing that'll make your proposal stand out. So for writing the science justification section, be thorough but concise. Seems like two completely opposite ideas. It's difficult to be able to write good, to provide all of the details that you need in order to convince someone who doesn't necessarily follow your research to understand why these observations are not only important for your work, but for astronomy in general, but without being overly verbose, too much flowery language, and too many pages worth of text. You want to cut to the point, have a relevant introduction and background information, assuming that the reviewer is not an expert in your field, but has a general astro background. Be sure to include all the relevant literature sources through inline citations or a bibliography at the end. Consider both the impact that a successful proposal will have, what the results could accomplish, but also what a null result might mean. If you wish to observe, try and identify spectral lines in a particular galaxy, what does it mean if you aren't able to identify those lines in your spectra? Don't assume, as I mentioned, that the referees know all the specifics of your research. Keep it a general background understanding with everything that you write. Also, don't blind with science. We get it. We're all astronomers. We know how important our own individual research is to us and to the field as a whole. Just get to the point and say the facts rather than necessarily the wow factor. Also, don't use words when a figure will suffice. If you can demonstrate with a figure, with a plot, exactly what you need in order to demonstrate why these observations are important, then do it. Reference that that figure in your text. However, don't add a bunch of superfluous pretty pictures just because you think it might entice a reviewer more. For the technical justification, make sure you're up to date on the availability of instruments that are going to be up on the telescope that semester, as well as their capabilities. Instruments can occasionally get upgraded or changed. For instance, X-band. So you need to make sure that you are aware that you are proposing to use tools that actually exist on the telescope. If you have any questions about details on an instrument, as we mentioned, if you are hoping to perform continuum observations, which can be a bit more complicated to set up, please reach out and get in touch with part of our observatory support staff, and we can help you to get the information that you need. Be sure to provide all of the information that is asked for. If reasonable, if possible, use the sensitivity and mapping calculators. They're there for you to use to make things really easy for you and for really easy for reviewers to validate your requested time, your requested setup. And related to this, be explicit about the assumptions you're making. Don't just say, we assume 30 minutes of overhead. Where are those overheads coming from? We want to know your thought process for every step so that we can verify that you are making perfectly reasonable and scientifically valid requests. Please don't ask for something like an instrument that isn't going to be up, or something that is beyond the capabilities of our telescope. Don't ask for an instrumental setup that is not justified by the science. You don't just want to tack on another receiver and another frequency just because you want to see what's there. You need to fully explain and justify all of these requests. And again, lastly, don't pad your time request. We do review with the information provided your requested time to make sure that it is reasonable, that you're not only requesting enough time for you to actually accomplish the sensitivity requirements that you're asking for, but that you're not just asking for a random amount of time to get whatever you think you want. So always be detailed and specific about how you got the values that you did. And a few more tips for the justifications. As I mentioned, these do not have a limit on the space that you can provide. So you can be as detailed as you need to be in order to get the information across. What instruments you're using, how and how long you're using them, where you got those values from, what the overheads are for pointing and focus. Depending on the frequency, you either want to perform a new pointing or focus every couple of hours, or if you're going really high frequency like Argus, you want to be able to go back point focus anywhere from every 30 to 40 minutes, as those values can change over the course of a night. Again, if you're doing higher frequencies, generally speaking above 30 gigahertz, factor in an auto OOF every few hours. And make sure that you are specific about how all of these overheads are going to add up to your total time. Slew times as well, also important to consider if you have multiple sources that are at different points in the sky. And then there's a few common mistakes that people don't really take into account when they're setting up their sensitivity or mapping calculations. Some of them were mentioned before, like the confusion limit. So this is based on the background sources in the sky. Once you get enough integration on the source that you want, any background light from stars is going to be equal to the noise that you're getting from empty sky. So once you hit this point, you're not actually going to be not likely to be getting any higher resolution data out of it. And the 1/f noise, this is an electronic component that is dependent on the bandwidth, the frequency that you're looking at, 1/f. So you need to be considering how these might affect what sensitivity limits you can receive and how long you can integrate for. RFI is a really, really important one. Unfortunately, we have still a lot of RFI here, even in a radio quiet zone. And we are working on providing resources available to you in order to readily check the RFI, much like we have the sensitivity and mapping calculator websites. But there are also other resources still available right now. You need to consider whether or not you are going to be trying to observe a line that is going to be completely obliterated by potentially a very frustrating Starlink satellite that happens to go right overhead. So consider those things, consider sources of emission, and have a plan with how you're going to deal with them if they exist. And of course, use the sensitivity mapping calculators. We have them there for you for that reason. For some different setups, say Mustang, we have other resources that may be better suited for you, but for most cases, these are fantastic at giving you estimates of the time that you need. Now, the proposals themselves are panel-based. The review of the proposals are panel-based, broken up into 8 different panels. And these consist of a broad range of members from the astronomy community, with no specific experts in one field associated with a given panel. Proposals are then ranked from 0 up to 10 being the worst, and then ultimately are graded given one of the following letters. So an A grade means you will be active for both the coming semester and the following semester, and it is nearly certain that you will be able to complete all of your observations. Group B is approved for only 1 semester, but again, it is still highly likely that you will get most, if not all, of the observing time that you request. And then group C, those also for 1 semester, but is generally considered filler time and will have a lower priority in scheduling. And finally, there are those projects that are not accepted. So we've come to the end. We have talked about a general overview of the GBT and the science that it is capable of. We've shown you the sensitivity calculator, the mapping calculator, and how you can take all of that information and submit it into the proposal submission tool. And now gone through a few good tips about how you can make your proposal stand out and hopefully not fall through the cracks. So at this point, I open it up to not only questions from my talk, but if there are any questions that you've had lingering or thought of throughout the entirety of the workshop, we are welcome to hearing those right now. Thank you very much.
Thank you very much, Jessie. Really good information for those starting out. So we had 2 questions that Tony has answered kindly. Please go ahead if you have any further questions. We have about 5 more minutes to discuss, and you can hang around longer as well. So we're open to your questions.
We also understand that this is a lot of information up front, especially for those of you who have not submitted a proposal before. So it's entirely possible that you don't know the questions that you will have, in which case that is why we are here. There is a help desk that you can submit requests to in case you do have any questions that come up while you're writing your proposal. Side note, we ask, please try not to write your proposal at the last minute. Don't be just logging into MyNRAO and trying to make a proposal the day before it's due. If you can manage it, that's great. But if you do run into problems, it's possible that we won't be able to get back to you to answer any of those questions in time.
Especially since this proposal deadline, that will be a Sunday night.
Correct.
So I know we'll have staff monitoring things, but it is much better to start this earlier rather than later. We'll just wait here for a minute or 2 to see if there are any other questions.
Sounds like people are mulling things over, or they feel pretty confident about everything that we've talked to them. So yeah, if you guys do think of anything, please don't hesitate to reach out.
Yeah. Well, thanks for attending, everyone. Thanks to the panelists for providing answers and presentations. And we'll catch you all on a proposal, we hope. So have a good rest of your day wherever you are in the world.
Take care, folks. Thanks for listening.